before we get started, I will also mention that this is part of a series of, I have to be careful with that word, I remember, of 3 sessions. Correct, Michiel?
Yeah. Pre-planned so far. It depends if there is interest and need to go further than I had planned.
Exactly. So 3 sessions on color. I will not say anything about that because luckily I will not be the speaker. That will be Michiel. And I think that concludes the administrative fun. So Michiel, the floor is all yours. Have a go.
Okay. So like David says, this is one of 3 sessions. This is the first one that we do about color. The idea of these sessions is to demystify color a little bit. Oftentimes when you talk to people about color management, you get reactions like, it's a beast, it's very complex, it's full of rabbit holes where you lose yourself, but it doesn't really have to be. And I wanted to take these sessions to start from the very basics and to build our way up to color management in print production. So today's first session is, where does color actually come from? What is color? And we'll start with that, and then we'll build up. Let's see, lots of colors here. These are the 3 sessions we have planned so far. So the first one for today, what is color? Then communicating about color, which is also a very important part. And then once we know all of that, we can make it into predictable color management. So let's get going. Like David said, this is a 4-piece cafe, so feel free to ask questions at any time, to ask me to elaborate. I'll try to answer as best I can. And if it's out of scope for the session, I will still try to answer you by email afterwards. That is no problem as well. So when we talk about color and color itself, there are really 3 big parts we have to take into consideration. The first part is the light source that is shining on the object. If the light is very yellow, the object will look very yellow. If the light is very blue, the object will look blue. So the light is important. Then we have the object itself. Of course, different objects will look a different color. So you have a red apple, you have a green apple. You know that these objects have different colors. Objects absorb and reflect different parts of the light, and that gives them their color. And then, of course, there is the person who is looking at the color, the person who is interpreting the color. Your eyes are taking this information and telling you, hey, this looks like this color. Your brain is interpreting certain signals. That's important as well, because all 3 of these elements have an influence on the color that you identify. So I'll go through these one by one. First off, light. What is light? Light is just electromagnetic radiation. The thing that we call light is basically a part of a huge spectrum of radiation. And then we can identify standardized sets of radiation that we call standardized light sources. If we look at the electromagnetic radiation, there are immediately some words that we recognize. For example, we see on the very left, the waves with the most power indicated here are gamma rays. Gamma rays is what made people into the Hulk, right? So that's one kind of radiation. On the other end of the spectrum, we have radio waves that bring you your radio presenters in your ears. We also have microwaves. We know all of these words. We know all of these things that are helpful in our lives. Then you see in the middle, we have visible, the visible spectrum. So light is essentially the visible spectrum. It's just a part of all of these waves, which are basically just different wavelengths of the same radiation. The area of wavelengths between 400 nanometers and 700 nanometers is what we consider light. Now, actually, it's more like 380 to 740 nanometers, but to make it simple, we round those numbers. So the visible spectrum, we have 400 to 500, which we will consider blue, 5 to 6, which we will consider green, and 6 to 7, which we consider red. Again, obviously, that's not the case. If we look at the area right next to 5, it's still kind of blue there. The reason we define these areas is, again, to make it simpler to understand what you're looking at. The visible spectrum is really the rainbow, right? If you put light through a prism, you get all the wavelengths nicely spread out for you, and you see the visible spectrum. So all of those colors are present, and they're all identifiable by a certain wavelength, which will make it simple, and we look at the primary colors. So what is white light? White light is just a combination of all those wavelengths. If you have an equal measure of all the wavelengths of visible light, we consider that white light. Again, if we break that up into our separate primaries, the radiations we identified, each set of 100 nanometers in wavelengths, we have our red, blue, and green, and we mix those, we see white. People often get a little bit confused by this point. Why is that? Because we're used to kindergarten class where we mix paints together, and the more paints you mix together, the darker the color gets. Now, that is called subtractive mixing of colors. With light, we are doing additive mixing of colors. Of course, if we have one light source, we have a certain amount of light. Now, let's say we take one light source and then we add another light source. Of course, light plus light equals more light. So the resulting color will be lighter. And that is why our primaries are actually darker colors in our additive mix. And the more light you add together, the brighter the result will be. And we end up with white light. Now, of course, we can't just start talking about, oh, let's use some white light and say that's the correct way to identify something. We have to be very precise when we talk about our light, because as we said, it has a certain influence on the color as a whole. So standard illuminants were identified. These are radiation, there are sets of radiation, combined wavelengths, that present a standard illuminant to which you can reference, and everybody knows which wavelengths are included and what the resulting light is. The graph you see right now is showing us the strength, the amount of radiation of each wavelength included in our light source. So our standard light source D50 includes a certain amount of wavelengths of 380, a certain amount of 500, and so on. And we see here by that graph how much of each wavelength is present in our light source. There's more than one of these illuminants. We also have, for example, the D65. And if you remember our earlier visible spectrum slide, we had that RGB at the bottom, R on the right and blue on the left. You can see here by the graph how much of each primary is included in our light source. So we can see that, for example, with D65, there is more blue in the light source than we see in D50 and less red than we see in D50. So we can assume that our D65 light source will be a bluer light than our D50 is.
But the standards, Miki, that you're referencing here are intended to look like daylight, correct?
Yes, so these are supposed to be standardized daylight illuminants. The D50 and the D65 reference specifically a certain color temperature, 5,500 and 6,500 Kelvin, or 5,000 Kelvin and 6,500 Kelvin, which is a white and a bluer white color. I can go into the whole history of where those Kelvin color temperatures come from, but I didn't add that slide because it went a little bit too deep. But these are not the only ones. We don't have to reference standardized daylight. We use these because when we judge print, when we judge stuff, we judge it normally in a certain standardized environment, which is our daylight. Another illuminant which has been standardized is incandescent light, which is called A, which is a very red light. You can compare it to candlelight. It's about 2,700 Kelvin if you want to stay with those numbers, and that's very red. Now, of course, we won't use incandescent light to judge our print because it's very red. You see, it contains almost nothing in the blue area. So we won't see any blue color reflected on our objects. So those are some standardized light sources. These are theoretical, but they reference standardized daylight. So once we have these light sources and we say we standardize our light sources as D50, D65, FA, there are a few of those. We know what we're talking about on light. We have identified which wavelengths of radiation we know are in our light. So as long as we all talk about the same thing, that is no longer a variable. That is something we can rely on. Then we have our objects. Now, any object will absorb and reflect certain wavelengths, and that gives them their color. And in nature, we know that many things have adapted to that specific feature, and they do things to do that. For example, there is a certain bird that has very, very blue feet, and they have developed those very, very blue feet to attract mates. So they have evolved in a way that gave their feet a certain blue color, so they absorb and reflect certain wavelengths of light to make that a feature that works in their advantage. And there are many things in nature that work that way. So let's look at some objects. For example, I have, and I'm prepared, I have an apple. I have a very red apple, and I have measured that apple with a D50 illuminant, and that gives me this spectral reflection graph. Now, we see, if you remember again, the RGB on our graph, that our graph shows a very red color. There is a lot of reflected power here on the right side of the graph and almost nothing on the rest of it. You see there is still some light present on the green and the blue areas in the graph. Does that mean that this apple is also sort of green and blue? Well, yes and no. These wavelengths are present, but equal amounts of our primaries give us white. So that means that if we draw a line here between the 0.1 and 0.2 areas of the graph, that would give us white light. And then we only see more on the graph on the red area, which is why my apple is completely red. And, oh, David?
So the parts that you have on the left will help to illuminate the apple, but they are not going to change the color that it shows.
Exactly. So even if that area was here over the middle, somewhere on 0.4, it would still be a red apple. It would still just be a lighter red apple because we would have more white light and then a bit more red. So it would be light red, but it would still be red. It wouldn't be more blue or more green. Now, I have also other objects. I have this tan coffee cup, and this coffee cup, if I select it on the right, we see a reflective graph. And since this is a kind of yellowish brown, we see that we have a lot of green, a lot of red. Again, everywhere where we have an equal graph will be considered white. Then we see that there is more on the green area, but there is also red there. So that's yellow. And then we have a bit more on the red side. So it's kind of a reddish yellow. And that is pretty much what this cup is. It's a brownish yellow color. And I have a third object, and that's my phone case. My phone case is kind of teal. It's a cyan, kind of. And we see the graph has a lot of blue and a bit of green in there. So that's kind of the color we would expect. Now, all of these have been measured using a standard illuminant D50. So daylight, which has a lot of light in each part of the spectrum. Let's change that illuminant. Let's go back to our apple. And let's change the illuminant from D50 to A. We see immediately the graph changes, the reflectance graph. Why? Because obviously my apple cannot reflect light that isn't there to begin with. So where my D50 light has light all over this area, the apple is able to reflect that light if it doesn't absorb it. If I change my lights, I don't have all that extra radiation anymore, so the apple can't reflect that. It only reflects what is present. So my curve flattens a little bit here. It loses this peak around the 640 area. Now, this is more obvious if we look at a different object. Let's go to my coffee cup. We see this curve is pretty close to the apple. So does that mean my coffee cup is now the same color as the apple? Well, with that light, yeah, it's pretty much the same color as the apple. If I change back, we see that I lose all the blue and green that was there, and it turns into orangey red. So my coffee cup has changed color. And even worse, if I look at my phone case doesn't reflect anything anymore, because all the light I had that was reflected was part of the blue area. So since I don't have any blue light anymore, there's barely any reflectance, so my phone case, when illuminated with incandescent light, will become gray. And that's a bit what happens with the object. I have another slide that shows, there we go, that shows how that works. It's basically just mods. When you have a curve like this, you can multiply it by the reflectance curve of your object, and you get the resulting curve. So what does that mean? That means you can always recalculate your light source if you have enough information. So if you measure your objects with all the light, essentially, and you have another light source that has less light in certain areas, you can recalculate what your object would look like with a different light source. And this is actually used in many cases in colorimetry. So that is how our objects are influenced by the light. So
you can see that very obviously in the yellowish street lights, how the cars change colors.
I was going to go there, but you're there first. That's a really good example. If you have a car on the street and you have a silver car and you go outside during the day, that car will look silver. If you go outside in the evening with very orange street lights, that car will look orangey red. But there is an extra factor there, and I'm going to get there when we look at the next slide, actually. The third part of our equation here, after light and objects, is the people. And the bottom title we see on this slide, Chromatic Adaptation, is another part why this changes. If you make that picture of that car, you make a photo of it during the day and in the evening, it will be silver and orange. If you look at it and you go outside in the evening, it might be that for you, it still looks gray. Why is that? Because of chromatic adaptation. If a person is in a certain environment, it will neutralize the color. Your brain will neutralize the color to what it sees as white in that situation. Another good example of that is when you go skiing, for example, and you put on your very tinted goggles that have a very yellow tint, you will see yellow snow for just like 1 minute, and then everything will become white again. And when you take them off, it will be very blue for a minute, and it will go white again. And that is how our brain interacts with that color as well. So here we are also a certain influence. Now, people. How do people see color? Well, in our eyes, there are two types of photosensitive cells. So cells in your eyes which are sensitive to certain wavelengths of radiation. We have rods and we have cones. The rods are sensitive to the level of the light. How much light do you get? So basically they're seeing in black and white. They're very useful in low light conditions because they don't require a lot of light to work. And that's why in the evening, when you don't have a lot of light, you're seeing in grayscale. You're seeing everything a bit gray. Then, once you have more light, the cones take over. And you have three types of cones. You have types which are sensitive to the three primary colors here, red, green, and blue. So depending on how many of those cells are activated, you will interpret all the electrical signals as a certain color in your brain. That means that if you have a different way of sensing the radiation, you might have a broader spectrum and you might have more visible light. We know that some animals have a different area of the electromagnetic spectrum that they're sensitive to than we are. Also, if you make videos with your phone camera and you video a infrared signal, you can actually see that signal with your phone camera because it's sensitive to that infrared part of the spectrum. We are sensitive to these areas, which is why we can see color the way we do. Then, of course, not every person is the same. Every human is a bit different from every other human, and there are nature and nurture elements there. If you look at nature elements, for example, some people have color blindness in different ways and on different levels. So they see and interpret color in a different way than we do. There are also nurture elements based on culture, based on language. There are different ways of seeing color. David gave a good example during a call we had earlier. If you have Inuit people, they have more words for white because they live in a white environment and they can judge different colors of white. Another interesting thing is, for example, that the color blue is always the last word added to a language when a language originates. If you look at the written works by Homer, he uses the color blue not even once in the stories of the Odyssey, for example. Even though a lot of that book takes place on the sea, he never mentions blue, which is kind of weird. But that's because blue is only added to a language at a later stage. There is also not often a blue pigment available in early stages of evolution. So that is also an interesting feature. So we have to do something to average that out, to know what an average human would see color as. And that's where the CIE Standard Observer comes in. Now, what they did in 1931, around that time, they did a whole lot of tests to see how people would identify color. We already know, because in the earlier slides we talked about primaries and about light and radiation, that we can identify three primaries. We can identify red, green, and blue as primary colors. Now, that means that if you provide certain amounts of light in each of these primaries, you should be able to recreate every color, right? Because that's all the colors we have. So what they did was exactly that. They had a color and they tried to recreate it just by changing the levels of the primaries of red, green, and blue. And every time they had a match, they wrote down those numbers and they tried the next color. And they had a whole lot of people do that exact test. Then they had a whole lot of curves, and then they averaged that out. And that brought us these color matching functions. Now, these have been normalized to max out at 1 when you combine them. There's a bunch of stuff that has happened with these curves to make them work mathematically. But in the end, they end up with a value for RGB, or in this case, X bar, Y bar, Z bar, that results in a certain color. So if we look, for example, around here at the 475 nanometer mark, we would need a certain amount of red, a certain amount of green, a certain amount of blue, and that would result in the color that we would see at that wavelength of radiation. And because of this, because of the work they put in to create these curves, we now have mathematical data on how humans interpret wavelengths of radiation as color. And that means we now have mathematical data for a standardized color source, being the light. We have mathematical data for our object because we can measure the spectral reflectance of objects, which is this curve for the apple. And we have mathematical data for our human observer, which are these three color curves. With all that together, that means that from now on, we know what color is. We know how a human sees a color. And that brings us to the start of actual color management, because we now can, with just a simple measurement device, identify a color and then use that information however we want to use it. So that actually went a lot faster than I thought. This is what we wanted to cover in the first cafe. We went all the way through the history of, what is light, a bit of physics there, how the objects absorb and reflect light, and how our eye interprets that light as certain data. Next time, and that is 2 weeks from now, we will talk about color communication. That's also going to be an interesting one. It will explain why we don't speak about apple red, for example, when we're trying to tell someone what color we want to use in print. Or we don't say sky blue because the sky blue is different wherever you are on the planet. So all that information is going to be useful to help us identify and name colors, and that's what we will cover 2 weeks from now in the next session about color.
If someone has questions, now would be a good time to ask. I will start off because I have one. If you go back to the observer one, where you have yeah, that one. What you're talking about here is average data, correct? So it is not necessarily going to correspond to what anyone sees, but it's the average of what a whole lot of people see.
Yeah, so a whole lot of tests were done with a whole lot of people who were all asked to identify, to recreate a color that they saw with a certain amount of the light. There is I read some really long and interesting articles about how all this worked, because we're talking about units of light, right? We're talking about units of red, green, and blue. And what one unit is, like talking about the units makes it very easy for people to say it's 94% of a unit of red, 40% of a unit of green. But what does that mean? How many lumen of light is that? How many photons are we firing at this target? That can all get a bit complex. All of that stuff has been normalized to mean that 1 unit of red, 1 unit of green, and 1 unit of blue together is white. So however much light you need of each primary to end up with a white total is 1 unit. And then you divide that up in percentages with a slider or whatever to recreate that color. Now, there were 2 sets of tests done. A test where you have a 2-degree standard observer, and people who are working with color management have heard that before. There is a 2-degree and a 10-degree observer, because we have noticed that when looking at a small area or looking at a big wall in front of you, color is identified differently. I might not think that, I don't actually have a good example, well, maybe this. I might think that this is a nice color, but if I painted my whole wall with this, it would be a bit overpowering for my living room. So all that is important.
That's why this concept of having a tester that you take home and you paint part of the living room wall is only limited in application, because it's hard to translate that to what it means on a whole wall in the end.
Yeah.
But so what you're seeing here, and that was the question I was trying to get to. What you're seeing here, if there is discussion on the internet whether the dress is what was it, green or blue or gray, that is what you're talking about here. Each observer is going to see something different depending on also physiology, I guess.
Yes and no. The whole dress conspiracy is actually caused by a different phenomenon. That's actually, partly this and partly the white balance situation. I already mentioned the fact that you see blue and white with your ski goggles. That's partly caused by that. That photo was taken with a very bad white balance under bad conditions. So however you make that photo will influence what color you see. If they had made that picture in a well-lit room with a good white balance, we would have seen the right color from the get-go. But it was slightly off. And that makes it so each person starts their own chromatic adaptation to identify the color. And depending on what they see around it and everything like that, you see a different color. And then obviously, if you decide that one of the two colors of the dress was neutral, so either the area that would be considered black or blue, I think, or black or gold, if you decide that area was neutral, then you would see it as black, and then the rest of the dress would become blue. And if you decide that the area that you saw as blue was neutral, then that would be a white dress, and that would turn the other area to gold, I suppose. So that depends on what you see as neutral, and you change the other parts to fit with the neutral color.
One more question, and then we have one in the comments as well. You showed daylight, so D50, D65.
Yeah, I'll go
you
back to that
also
slide
had
as well.
Incandescent, which is a candle, correct?
A candle, a light bulb. It's a very orange light. I think many light bulbs have 2700 Kelvin as well.
Yeah, so that was my question. If you look at the standard light we would have, that would be somewhere in between the D50 and the A, I guess. Most of the other light sources.
Using daylight as your judgment color light space for print is actually kind of weird, because in many situations we're not using daylight. We're not reading our papers outside, we're reading them indoors, and we have different kind of light bulbs. We have incandescent light bulbs, we have halogen light bulbs, we have these TL tubes of light bulbs. There are standards for those as well, like TL light, I think, is close to F as a light source, an illuminant, which also exists. But the advantage of using D50 or D65 is that we cover a broad range of the spectrum, which means that we are kind of identifying everything, starting with a bunch of wavelengths. There is even a fictional light source, which is called E, I believe, that has an equal amount of every wavelength in it, which can also be used. But of course, that's not realistic, because then you're again looking with light that doesn't exist. So it's always a bit of a trade-off. And usually daylight is a very good judgment.
The D50 is closest to daylight, I think. You see the curve is kind of flat all the way. So it's the best white one.
Yeah, there as well, if we again go in the direction of objects, we have a bit of a discussion, because in paper, oftentimes to make paper appear whiter, they add optical brightening agents, which is a chemical product that translates UV light into visible blue light. It's a bit like those tiny blue things you find in washing machine powder. That makes everything appear whiter. But we don't see that light in advance. So we have to take into account parts of the spectrum, part of the wavelengths that we project onto something, the invisible part as well, because it might become visible when it hits an object. And in that case, D65 would give us a whiter result, because there is more of the UV area, more of the blue area here present than in the D50.
I think that's one of the things that people don't always realize when they want their washing to be very, very white, is that you actually put chemicals on it that transform UV light into light so that it looks whiter. So you're actually making it dirty. There was one question about the Homer, and that is not Homer from The Simpsons, but the Roman writer, I guess.
Greek writer, I think, yeah.
When does blue appear in a language? Is it linked to something? Do you know that?
I am not sure, honestly. I read originally I was going to tell a different story when I was talking about color and human interaction with color, but when I researched it in more detail, I found the story had been partly debunked as sensationalism journalism, and they had kind of embellished the story to make it cooler, and I didn't want to be here telling lies, so I decided not to go with that story. And instead, I looked up something else. And it turns out that when a language develops, of course, words are added to a language as it develops. And in many languages, it has been seen that blue is one of the later words to be added to a language. And part of that is because there is no pigment available for blue early in a civilization. It's a harder pigment to get, so it takes a while longer for people to start to name it, I suppose, as a color. While if you have that available in your language, in your world, it would be earlier, it would make more of a difference. For example, if we look at those texts in Homer, I think I remember the amount of times the color was mentioned. Red is mentioned quite often. White and black are mentioned less. And blue was mentioned 0 times. Then again, sheep are described as purple, which is also kind of a weird thing to do. But, you know, things were different back then.
Yeah, sheep have changed a lot then.
Yeah.
I think I would prefer the purple variant. Any other questions, people?
Yeah, I have one thing to say about the viewing light conditions. When I was working in a print shop as a pre-press manager, we always, the customer were usually sent the proofs to their home in the evening, and because we were going to print it in the morning. So they looked at it at the bed light or something, and we always got the response that, well, it is too much red, because they watch in a red light. So we knew that we could ignore what they said about the red color.
Yeah, viewing conditions are important, and I was at a customer not very long ago, and we were there for color profiling for their printers, because the print was too blue, and I had a similar thing that I had with a different customer a year ago. They said, "Oh, when I print this image, it's too blue, or it's too green, or whatever," and they're printing a very gray image. But to look at the color, what they did was they printed the print, they took it and they put it on a flat surface they had available. And that flat surface was the big blue mat on top of their cutting machine. So they put their gray print on a blue mat, they look at it and they're like, this is too yellow. Well, yes, because you're standardizing your vision with the blue. And actually, I had the issue a bit when I was working with my slides. If you remember the slide that I had about the cones and rods, the rod is actually, I promise you, 40% gray. But on the screen, with all the green around it, it turns out to look purple. Mm-hmm. For me, anyway, when I look at it.
It is purple, yes.
Yeah, so it's actually, when I selected the color, it's 40% gray. So it should be perfectly neutral, but it isn't, because we change our vision. And I had the same thing with that customer. They said, hey, yeah, our printing is too blue now. And I remade the profile from scratch, and we printed a new test and we put it together. And I asked for a reference to compare it to that was good in their eyes. And they put a reference there. And my print was bluer than their print, but their print was fairly yellow in my eyes. So it kind of bounced in between. Mm-hmm. So if you make your judgment and you base it on a random factor, then you're never going to get there. And if you print all your grays and you put them all in a big pile and you pick the best one, then everything else is going to be yellower or bluer or greener when you look at it.
That's why you should judge in a gray environment and not in a blue or a green environment.
Yeah, that's why you have those standardized light booths with these special light bulbs that give off exactly the radiation you want. And you're supposed to have those in a room that has neutral colored walls, and you're not allowed to wear this shirt when you look at it because it's very colorful. You're supposed to be kind of neutral when you're looking at those prints. And then when you send it to the customer, they're going to look at it on their laptop screen and they're going to be like, this is kind of not what I was expecting, because they're looking at it on their laptop screen in their brightly colored homes, and they're judging what they see on their screen. So there's always a communication issue there. And that's a really good segue to the next session again, because that's where we're going to talk about communication. If you talk about color with customers, then you're supposed to talk in terms that everybody understands. And there's different ways of doing that. You have different color spaces, you have different color systems that you can use to name a color. For example, Pantone colors are very known as a way to name a color. But of course, if you use that way to do it and you use Pantone colors, then you have to be aware of what you're looking at. And many people have this really old Pantone book that they bought 15 years ago, and it has been lying on the window still in the sun for very long. And then they open it and they're like, this is the color I'm looking for. But if you take a new Pantone book, it's a different color because it hasn't aged as much. And then you're comparing it, and it has the same name, but really it's a different color. So there's different ways to communicate, and some ways are better than others. And that's what we're going to look into in the next session.
So one more question: if you send something, if you want color to be judged by someone that they don't have a line booth and all of that other stuff, what do you tell them? Go outside and look at it rather than inside, or?
Yeah, I suppose typically people tell their customers to look at it near a window instead of under their light bulb. It depends on what is your error of your margin of error, right? How far off is the customer allowed to be? Because in practice, they're actually the ones who are looking at the file in a more realistic condition than the printer, because we're looking at it in a very standardized environment. And the reason for that is because we have to be able to judge it based on maths. So we have to judge it based on standardized environments. If we look at it differently each time and judge it differently, then our judgment is worthless. So we have to standardize us. The customer is...
To play devil's advocate, if I'm printing something and I know it's going to be used in a supermarket, then I think I would be better off judging it in light that mimics the supermarket light as well.
Yeah, that's true. That's also a story that I've heard at some point, that you make your print to be very, very beautiful with your standardized conditions, and then they display it in the supermarket with those F standard lights that they use there. And suddenly the color looks awful, and that's because they didn't take that into account. And of course, that is the only time that people are going to be judging the color of an object, is when they're looking at it on the shelves and they're like, oh, this isn't a very nice color for a brand. So that, I'm sorry about that. When I'm in my presentation mode, I can't actually turn down that phone either.
But you don't want it to be, so you want it to look good in the supermarket. I guess if it's a label on a can or a bottle or whatever, you still don't want it to look really bad when you take it home either, because
yeah.
So you have to be careful which colors you use.
And we already spoke about essentially this slide, right, where we have the influence of light and what an object reflects. Now, there is another interesting part about this, and that's called metamerism. And that means that different reflection curves might, with certain lighting condition, at some point reflect the same curve, right? Because if I had a big spike with this A light on the left, then that wouldn't be visible when I'm looking at it in A light. But when I'm looking at it in the 50 light, that blue spike would be very visible. And there are certain materials that have that situation going on, that have a certain area of the spectrum that is being reflected from a certain light source, but that is not being reflected from a different light source. And those are called metameric materials. And that is actually being used for tests in some points to see if the light you're using is correct, right? You have these little label stickers that you can put on a proof, and it will have 2 strips of gray, essentially. And if you're looking at it under standard lighting, then it will be nice, even gray. If you're looking at it with the wrong lighting conditions, you will see these lines because that material is reflecting different colors. So that's a pretty cool thing that is also caused just by this physics phenomenon of reflected light.
Cool. Any other questions?
Or comments or concerns?
No.
Okay, if you think of something at some point, like I said at the beginning, or you want to dispute anything I said, you feel free to leave us a comment on our socials, because we're going to post this in places. as well as just send us an email. You can email support@fourpees.com. You can email me directly if you want to, and have my mail address. And you can just ask the questions you want to ask, and then I'll get back to you when I'll look up whatever I need to look up to properly reply to you. Now, the next session about color is planned for April 29th. That is about communication, about quantifying color, color systems, ways to communicate colors to each other. But before that, I don't want you to think that there is nothing in between. Next week on Thursday, we have a cafe about pricing engines in Elean's Presero, hosted by Helena. Which will talk about all the advantages of using complex pricing engines within your Presero webshop. So
Actually,
don't miss that one either.
We'll do both simple and complex, just the whole range.
So yeah, we'd like to see you in both of these. So 2 weeks from now, my color thing is continuing. 2 weeks after that, we'll have the last session I have planned for now. But like I said, if anyone comes up with any important or big questions that you want to ask and they're worth an extra session, then I might create an extra session with all the interesting questions.
So 4pees.com/events, if I am correct, and you will find a list of all the upcoming cafes, and you can register for those already. Normally you'll get an email with the link to the movie, to the recording, but it will also just be on our YouTube page where all of the other ones are as well, if you want to rewatch something else we did on color or any other topic. Thank you very much, Michiel. Thank you to the attendees for joining. If you have questions, let us know, and I am sure we will see many of you again next week.